Good morning, everyone. My name is Yassir, and I'm currently an AI engineer and PhD researcher at Ovalie Innovation in Lyon, France. My research focuses on weak signal detection in open data using dynamic temporal knowledge graphs. And today, I will be discussing two methods we have developed, iText2KG, which builds static knowledge graphs from raw documents using large language models, and Atom, which is a scalable, exhaustive, and stable version of iText2KG. And you can try the two methods by scanning the following QR code. Please, if you have any question, do not hesitate to drop it in the discussion, and I will answer them later. Our presentation is divided into 4 sections. The first section covers an introduction of our work and the main challenge we are seeking to solve. During the second section, I will present an overview of iText2KG, its key advantages and drawbacks. In the third section, we will see Atom, which is an advanced version of iText2KG that builds dynamic temporal knowledge graphs. And finally, the fourth section will be a hands-on building a dynamic temporal knowledge graph of OpenAI tweets using our library and Neo4j. As a context, the company I'm working with focuses on developing data-driven solutions, including transforming open data into dynamic temporal knowledge graph that would be a base for weak signal detection. And thanks to the zero-shot aspects of large language models, we are trying to explore their power in such a task. The LLM-based approaches for knowledge graph construction are divided into 3 paradigms. The first one is fine-tuning, the second one is ontology-guided, and the third one is zero or few-shot learning. iText2KG and Atom are specifically included under the zero or few-shot learning paradigms, which means that they do not require extensive training or predefined ontologies. So the main challenge we are tackling consists on building a solution that is a few-shot approach that does not require training or fine-tuning, self-guided without the need for ontologies, and a plug-and-play solution that can be adapted to different themes and use cases. Okay, now let's dive into the iText2KG method. The I actually stands for the incremental nature of our system as we build knowledge graphs step by step. The method includes 4 modules working together to build a knowledge graph, and we will see a simulation of them later. The first module is the document distiller. The document distiller reformulates raw input documents into semantic blocks using a predefined blueprint, focusing on relevant content to improve the signal-to-noise ratio and to guide accurate extraction. The second module is the iEntities extractor, identifies unique entities by comparing new entities from each document against a global set, ensuring all entities in the knowledge graph are semantically unique. The third module is the iRelations extractor, uses the local entity set as context with each semantic block to extract unique relationships. And finally, the graph integrator combines these resolved entities and relations into Neo4j. Okay, let's dive into iText2KG core algorithm. And let's take a scientific article as example. And the goal is to build a knowledge graph. iText2KG does not construct the knowledge graph directly based on the raw documents, but rather it selects important part from the input documents using a blueprint or a schema. The schema actually is not an ontology. It's a flexible blueprint guiding the large language model towards specific classes. For example, for this scientific article, we would prefer to build the knowledge graph based on the abstracts, the title, and the authors. Let's take this chunk as an example. The first step is to extract entities using the large language model, and we store them into the global entity set, which will serve as a reference set to ensure uniqueness of entities. The second step is to extract relations based on the previously extracted entities and the chunk as a context. And similarly, we store these relation names in the global relation names to ensure uniqueness. We do the same approach for the second chunk, but this time we compare the extracted entities and relation names with the global set using embeddings and cosine similarity. And the goal is to merge any duplicates and to perform entity or and relation resolution step by step. And voila, this is the knowledge graph constructed incrementally from these two chunks. We do the same approach for the third chunk, but this time we see that the entity item already exists in the global entity set, so we pick it up from the entity set. And to avoid duplicates in predicates, we have replaced it, uses and constructs with the closest one from the relation name set. And voila, this is the final constructed knowledge graph from the three chunks. iText2KG is like any method in the state of the art. It has advantages and drawbacks. As advantages, we can list there is no need for post-processing to resolve entities and relations. It is a zero-shot method, and the ontology is built incrementally. However, what we have observed is that the large language model fails to capture all key facts and triplets when the context is longer. And this is actually the forgetting effect. And this effect is an inherent bottleneck for the majority of large language models, including the private one and the state-of-the-art ones also. Moreover, the constructed knowledge graphs changes every time you run the prompt. And this is due to the stochastic aspect of large language models. And this is called stability issue. Moreover, incrementality is a key in iText2KG, but it significantly limits scalability. This is because the method must first build the knowledge graph and then compare it with the previous one before moving on the next chunk. And this induces more and more processing time. So unfortunately, iText2KG is slow. So to sum up, iText2KG is hard to scale. It has slower processing time, and it does not handle the temporal dimension. And when the documents are longer, it fails to capture all key facts. And of course, it constructs unstable KGs that changes every time you rerun the process. And that's why we have developed Atom. Atom actually employs a 3-module parallel pipeline that constructs and continuously updates dynamic temporal knowledge graphs from unstructured text. The first module, called atomic fact decomposition, splits input documents, DT, observed at time t, into temporal atomic facts using an LLM-based prompting with an optimal chunk size of approximately 400 tokens. What is a temporal atomic fact? Temporal atomic fact is a short, self-contained snippet that conveys exactly one piece of information. The second module, called atomic TKG's construction, its goal is to extract 5 tuples or quantuples in parallel from each atomic fact to construct the atomic temporal knowledge graphs while embedding nodes and relations. And the third module, called parallel atomic merge, employs a binary merge algorithm to merge pairs of atomic TKGs through iterative pairwise merging in parallel until convergence. And the resulting TKG snapshots is merged with the previous one, or with the previous dynamic temporal knowledge graph, updated at t-1 to yield the updated knowledge graph, or the updated dynamic temporal knowledge graph at time t. Now, let's look at a practical example. Atom actually uses dual time modeling, differentiating between when facts are observed and the temporal information conveyed by the facts themselves, which is characterized by a validity period. This separation ensures temporal knowledge graph dynamism and proper inference of relative times by providing the observation time as context to the large language model. So let's take this example. The first step is to construct atomic facts. Item build the knowledge graph based on atomic facts. So based on these temporal atomic facts, we build atomic temporal knowledge graphs. And atomic temporal knowledge graph, as you can see, they have, for each relation, they have a start validity time, an end validity time, and an observation time. And we choose to store this timestamp in lists to preserve the history of each information that comes to our knowledge graph. So based on these atomic knowledge graphs, we will merge them in parallel. And 5 days later, we will have another information to be processed, and we use the same approach. We perform atomic facts decomposition of this paragraph, and after that, we build the atomic knowledge graphs, and we merge them in parallel also. And the final step is to update the previous dynamic temporal knowledge graph constructed on the 18 November 2023. Voila. So we updated the temporal features of some relations in the temporal knowledge graph. And as a result, Atom demonstrates that atomic fact decomposition helps in getting 18% higher exhaustivity, 17% better stability, and over 90% latency reduction compared to baseline methods, including Graphity and iText2KG, using just 8 parallel threads and a batch size of 40 for asynchronous LLM calls. Now let's move to a hands-on practical session. I don't know if you have some questions, we can answer them now, maybe. Okay, so I will pick 2 questions. Okay, the question of Santosh Majiti. Hi, Yassir, the atomic knowledge graph rests in a different instance of Neo4j or in the same knowledge graph where the knowledge sits? Okay, actually the atomic knowledge graphs rest in the RAM. So before merging them, all the atomic knowledge graph are stored in the RAM. And after merging, the resulting temporal knowledge graph is stored in U4J or any other instance. If I still want, okay, are you doing anything to reprocess the same temporal fact to test the stability of the facts? I'm not sure to understand your question, Lily. But or what is the stability? Stability is just when you rerun the same prompt, the same process, you would have different TKGs. Okay, I will take the question of Wang. If I still want to incorporate some methodologies and rules to help the model better recognize, because I might need to build verticals, which requires some professional rules in this agent estimation and then defined elements. Actually, if you have some predefined rules, the best way is to extract or is to guide the large language model to extract specific information during the atomic fact decomposition. For example, if you would like to focus on the main results for a scientific article, you would prompt the LLM to extract all or just the atomic facts that describe this type of information. And this way you can guide and prompt the LLM to be very, very, very specific during the decomposition. Okay, thank you. Okay, now let's move to the hands-on practical session. So I will move to my Jupyter notebook. So we will build a temporal knowledge graph or a dynamic temporal knowledge graph of, sorry, based on OpenAI tweets. I have prepared some tweets ranging from 18 June to approximately 17 July. So the first step is to construct the atomic facts. For each post, we will try to decompose it into atomic facts. I have already done that. So to move quickly, I have prepared also the atomic facts. So for example, this is an atomic fact. OpenAI LLMs demonstrates the ability to reason. So the atomic facts is a small snippet that conveys exactly one piece of information. And the list of atomic facts, they have an observation date. And sometimes we may find that the atomic facts has also a temporal inherent information. For example, I don't know if I have some example here, but for example, here in this atomic facts, we can have OpenAI demonstrates the ability to reason on the 1st September of, for example, 2023, for example. So this is the difference between observation time and the inherent time. The second step is to build our temporal knowledge graphs based on these atomic facts. So I will import atom from ITX2KG, and to build the knowledge graph, you may need an LLM model and an embedding model. So here I have used OpenAI LLM model, which is actually based on GPT 4.1. And you can also use other LLMs. For example, you can use Mistral. So based on these atomic facts, I will construct the temporal knowledge graph. I have also processed that, and as you can see, we spent 10 seconds to build the temporal knowledge graph. I think we have 100 or something like that, 100 atomic facts. Okay, And after that, we send the temporal knowledge graph to Neo4j. So I will move to Neo4j. Okay. And as you can see, each relation has, okay, I will try to take this relation, for example. OpenAI podcasts are available for YouTube. Tack. And after that, we can see that the relation has an observation time, a start validity time, and validity time. So this atomic facts is atemporal. It does not have inherent time. So that's why the t end and t start are empty, but we have always the observation time. And this is actually the Unix format of um, the dates. And it has also embeddings, and we have stored also all the atomic facts that support this relation. So if in the future we have similar atomic facts, we would have a similar relation, and this atomic fact would be embedded or appended to the atomic facts list. And this is a very important way to verify relations in Neo4j. The most exciting part is that we can link this dynamic temporal knowledge graph with Claude using Neo4j MCP. So I will try to move to Claude. Okay. Okay, now I try to connect to my knowledge graph, temporal knowledge graph, and I explained what is the temporal modeling of our graph, because it's important to do that to let the LLM reason over your knowledge graph. And based on all that, I asked a question to return some insights about OpenAI based on this temporal knowledge graph. But I have a small issue with Claude because I hit the maximum length. So, but you can try the same. I will try to share the notebook in the iText2KG repository. And after that, after building the knowledge graph, you can try to ask questions, drive insights about this, or based on this dynamic temporal knowledge graph using Neo4j MCP and Claude. Maybe I would return to the questions. Okay. So in these 5 minutes, okay. Can I find this item in GitHub or other platforms? Unfortunately, item is developed by us, so we open source it only on our public repository. So it's not available yet on other platforms. Yeah, thank you so much, Jennifer. I have seen atomic facts don't fully cover the context because facts are produced by element. Yes, very, very good. Very, very good question. Actually, this remark is important when performing atomic fact decomposition. And what we have found is, I can come back to my, sorry. Yeah, this is one. If you see this figure, the A figure represents the exhaustivity of atomic fact decomposition performed using Claude, using GPT-4.1 and so on. And what we have observed is that the exhaustivity drops dramatically as the context or as the token count increase. So to have an exhaustivity superior than 18% or 80%, you need to have a small chunks. All your chunks need to have or do not need to surpass 400 tokens when performing atomic facts decomposition. And as you can see here, for example, GPT 4.1 is very good on doing that. The same thing for Claude. So the main idea is atomic facts decomposition. You need to use small chunks to perform atomic facts decomposition. I don't know if I answered your question, Rajan. Okay. We have 3 minutes. Yeah, exactly, Rajan. So small chunks leads to a better atomic facts decomposition. Or you can fine-tune an LLM model specifically for atomic facts decomposition. And I think this is a better approach. Can I convert documents in other formats like PDF, PPT into text files? So you can... Yes, you can use, for example, LangChain to convert PDFs into text. And after that, you may use Item to build the knowledge graph. And you can use Item to build static knowledge graph also, because it's just a special case for for temporal knowledge graphs. So for this static knowledge graph, you would have empty timestamplets. The same notebook. Okay. Yes. Poor Basha. Yes, this is a very good question. The thresholds are some way hard to manipulate, but what we have done is I can come back to my presentation. Sorry. Okay. We have generated pairs of similar entities and also pairs of relationship entities. And we used an embedding model to calculate the cosine similarity of these pairs. And we have estimated the threshold for entities is approximately 0.7, and the same thing for approximately for the relationship. I have taken the upper limits to not merge entities that they should not be merged, because this is very, very, very dangerous. Okay, we'll come back to does average input campaign biddings? Yes, actually, during the merge, we use the entity label and the entity name. The two embeddings are used during the merge, because we may have Apple as a fruit and Apple as a company. Thank you so much for having me. And if you have any question, remark, you can contact me via LinkedIn, or you can drop an issue in the GitHub repository. Thank you so much.